All right, so today we're going to continue covering the optimal binary search trees that we briefly introduced last time. Just to understand this a little bit better, let's look at a smaller example. Basically, the idea is that you're given this set of keys and a known probability distribution on it. So it's different from a binary search tree or a balanced binary search tree in that the keys are basically, they're still ordered. And so you've got, A, B, and C, and you need to adhere to the binary search tree properties. But you have this known probability distribution that some search terms, some things in this tree are going to be more commonly searched for than other things. For example, baseball is far more common than Shinty, or something like that. And so what you want to do is you want to optimize for the expected or the average number of key comparisons. So for example, if we just had 3 keys, right? If we had, say, A, B, and C. These are our keys. And suppose that we had a probability distribution on this of, say, 0.6, 0.3, and 0.1. Right? Now, if we just blindly did this as a balanced binary search tree, then we would have something that looks like this. B, A, C. It's a perfectly balanced binary search tree. But with respect to the probability distribution, it's not that great, right? The expected number of key comparisons that we would need to make in this is going to be A, B, C. Number of comparisons, comps, is going to be, well, for A, I have to compare it to B and then go down here and then find A. So that's going to end up being 2 comparisons. Likewise, C is 2 comparisons and B is 1 comparison. And when you multiply that by the probability distribution, right? I think that the total here is going to be what? 1.2, 1.5, 1. What is it? 1.7, something like that, right? Can we do better, right? Well, by observing that A is actually the most common search term, what we could do is we could say, well, we could go ahead and skew this tree a little bit, right? We could say that A is here, right? And then we could skew B and C over here in this subtree. And then we would need to determine, well, what would the root of that tree be? Let's go ahead and try B first, right? Or C first, let's say. Meaning that B ends up having to be over here, okay? What's the expected number of comparisons now? A would require 1 comparison now, times 0.6, the probability of searching for A. B would require 1, 2, 3 comparisons, 0.3. And C would only require 2 comparisons. Right? And you sum that up, and what do you get? What is it? 0.6, 0.9, so 1.5, 1.7 again? We didn't gain anything. Right? So one more try here. Yeah, go ahead. Yep. A, B, C. In other words, no better than a linked list where you're putting more common stuff up front, but still in a sorted manner because of A, B, C here. And this achieves 1.5. I'll let you check that out. Basically, you're just flipping these two around, right? That there's 1 comparison for A, that's 0.6. 2 comparisons for B, that's another 0.6, and then 3 comparisons for C, that's going to be 0.3. Right? So that altogether, that is 1.5 here. Okay. So what we want to do is we want to come up with a dynamic programming solution to find the optimal binary search tree based on an input probability distribution. Okay. What if we were just to try every single possibility? With only 3 keys, how many possibilities are there? There's a tree that looks like this. There are the 2 trees that we just looked at that look like this. And then the tree that looks like this. They're mirror images, right? So going over there, and then finally 1, 2, 3. 1, 2, 3, 4, 5. Is that all? Yeah, that's it, I think. Right? 5 possibilities. Not that bad, right? Well, in general, if you have n keys, then there are going to be C sub n, which is the Catalan numbers, 1 over n plus 2, 1, excuse me, 2n, choose n, possible binary search trees. So is that at all feasible to try every single possibility? No. Again, these are called the Catalan numbers. If you ever take, I'm sure that they still offer it over in the math department, combinatorics class, right? Where the basic combinatorics that you're probably already familiar with are, n choose, right? Combinations and permutations. There are a whole bunch of other different things that you can look at, and various sequences or formulas like this, like the Catalan numbers, right? And the Catalan numbers themselves have dozens and dozens and dozens of equivalent interpretations. For example, the number of binary search trees. What else is there? Not off the top of my head, but in my notes here. The number of balanced parenthetizations of operations, which is equivalent to binary search trees. A bunch of other things as well, right? But otherwise, how would you characterize this? This is going to be order. Well, if you pull out Stirling's approximation, you can get something like 4 to the n over n to the 1.5 or something like that. In other words, it's going to be exponential. There's no way that you can examine every single possible tree. Right? Just like the motivating example that we did over here, right? There's no way that you can recompute every single possible value over and over and over again and expect it to work. So what are we going to be cutting out here with our dynamic programming solution, with our memoization step or something like that? We're going to be cutting out things that are completely irrelevant, right? So first of all, suppose that I have keys K1, K2, K3, ... all the way to Kn. You first need to make a first choice, right? What's that first choice? Oh, sorry. What's that first choice going to be? First choice. Well, what was my first choice kind of over here, right? What's my root, right? My first choice would be either A or B or C, right? So my first choice here is going to be which key is the root of the tree, right? And I have a lot of choices. It could be K1, right? And then, completely skew it to the right, or K2, or K3, ... right? Up to Kn, KL, ... Kn. Right? So I'm going to have to examine all of them, right? You will examine all n possibilities. But we're not going to be able to do that recursively, because if I consider all n possibilities, then what does that leave me with? Suppose that I've got K sub L here as my root. Okay? Now what's in the left subtree and what's in the right subtree? Oh wait, I want a triangle here. There we go. That's going to be K1 through KL minus 1, all of those keys. And then I've got KL up here, and all the others end up going over here. KL plus 1 through KN. Okay? Now, if I did that recursively, then I would have to, there are n choices here. Down here, there are n divided by 2 choices, n divided by 2 choices, roughly, right? Of course, it's going to skew left or right, depending on what your choice is over here. N divided by 2 choices, n divided by 2 choices, et cetera, et cetera, et cetera. Right? If I multiply all of those together, it's going to be, too much, right? So I'm not going to be able to do every single possibility recursively, but I can set up a recurrence, right? Let's C sub I, j, be the optimal number of average comparisons involving keys I or KI through J, right? Now, I don't have an idea of how to do that just yet, but let's go ahead and understand why that would be a good thing to have. What is my full solution? The global optimal solution is going to involve K1, oops, let me write it larger, K1 through Kn. So, therefore, C1n is going to be the optimal solution. That's what I want to compute. Okay? Now, what are some other things that I can observe? For example, what is the average number, if I just have K3, for example, right? And it's all by itself. There are no children, right? There are no children over here. There are no children over here. What is the optimal number of comparisons needed to find that node if it's all by itself? One comparison times the probability of K3, right? So let's go ahead and write that out as 1 times P sub K3, or I'm going to go ahead and replace this with S to make it more general. It's not just the third one, it is some S. Okay? So we've already got a base case here. Right? What is the value of C sub I for all I? It's going to be the probability of searching for K sub I. Right? Probability of searching for Ki. And now remember that there is a 1 there, but I'm not even going to write it. Right? How many key comparisons do you need to make for an empty tree? For example, C sub, let's say I minus 1. That's going to be keys I through I minus 1. So here's I, they're the same, right? If it's 1 and 3, right, then that's keys 1, 2, and 3. But if it's I, then that's 1 key. If it's I and I minus 1, right, then how many keys is that? Well, negative keys or no keys. That's how we're going to interpret that, right? 0 equals no comparisons for an empty tree. If you could actually build a tree where you would get a negative number of comparisons. Wow. Bitcoin mining forever, because then it's like, that would be like running a Bitcoin mining operation that generated power as well. Like, that doesn't make any sense, right? All right, so those are these are my 2 base cases. These are the base cases. If I were to do this in a recursive manner, then that's where the recursion would end, right? When you're getting down to either 1 key, right, in which case you return the probability, or you've gone past each other, kind of like binary search, left and right, and you've gone past each other and you return false, you didn't find what you were looking for. Right? So now what I need to do is I need to come up with a recurrence. C sub I, j. Right? Well, again, remember that you're going to have to ask this question for each possible key. For the what if this one were our root? What if this one were our root? What if this one were our root? ... What if this one were our root? And so this is just a generalization of that at some point in the algorithm. Let me go ahead and pull up OBST is here. Where are we? There we go. I want my tree. There we go. There it is. All right. So this is involving K1I through Kj. Now suppose that KL ends up being our choice. For L running from for I less than or equal to L less than or equal to J, right? We're going to find the minimum. Remember, we're trying to minimize the number of key comparisons of something. Right? We'll come back to this here in a second. And then there's some expression over here. right? So what is the cost? Oops. What is the optimal cost of this subtree right here? What is the optimal cost of, or the optimal number of comparisons for keys I through L minus 1? Well, we have an expression for that, right? This thing right here. A recursive expression. C sub I through L minus 1. Oops. Let me undo that. 1. There we go. What's the optimal cost of this subtree? C sub L plus 1 running through J. Now, what's the cost of the entire tree? It's the cost of this tree plus this tree. But you also have to have some kind of non-recursive cost. The interpretation here is that there's a cost to this tree, there's a cost to this tree, but by putting this node in between them, you have increased the depth of both of these trees, right? And you've added a cost of 1 to search for this guy right here. So this will end up being a sum. Let me erase this. Of all the probabilities of elements, S is equal to I up to J of the probability of searching for the S key with a 1 right here, 1 times, but I'm not going to write that. Again, why is that? Well, you're building this tree, right? And this tree was of height H before. This tree was of height H2 before. And now by putting something in between them and putting them down further, now it's of height H plus 1, H plus 2. Or H plus 1, sorry. H2 plus 1. And you've got to search for that guy as well. In other words, you're increasing the cost of each one of these keys in the entire tree, which is just a simple sum. Yeah?
So we're doing that for every single...
For every possibility right here. Right?
Building a whole tree
Well, we're not building the tree yet. We're trying to find the best tree, right? In other words, this question is among keys ki plus 1 ... kj minus 1 kj. Which one should be the root? And that's what you're doing right there. Suppose that it's L, right? And then that becomes your root. You have to shove everything down here. You have to shove everything else over here that's greater than it. Right? Yeah?
Is there a reason we couldn't just do like the algorithm to solve this? Couldn't you just sort the probabilities in descending order and you just put the highest probability at the top?
Okay.
That work?
Let's go back to this one. 6, okay, so let me erase all this. Let me permute these. 0.3, 0.6, 0.1. So your proposal is to be greedy and go with B, A, C. Right. B would be the root, and then A and C. Does that look like a binary search tree to you, though?
Well, you put A as the left child of B and C as the right child.
Yeah, but then now you're back to the original one that I had up there, right? You need to ask yourself you can't sort by the probabilities because you've got the keys and you have to preserve the binary search tree property, right? So A is less than B is less than C, right? It has to be a binary search tree among those. Right?
You can't compare the probability.
Now, yeah, I mean, you're not going to be able to. Maybe by greedy strategy, you mean that to choose highest probability
So if the probability
as the root.
and the probabilities were the keys, this would work. But
Right.
if the keys are something else.
This is a
Yeah.
binary search tree.
Exactly. So, what was the original? The original was 0.6, 0.3, 0.1. That's kind of I think no matter what, I think the greedy strategy will work with that one, right? Yeah. but if you change this slightly so that it's you want, let's see. You just need to make sure that it's larger than the other two, but the other two are roughly even. So 3, 3, 4. 0.3, 0.3, and 0.4. All right. So yours would be A, and then B or C. It doesn't really matter, right? Because they're equal, and that would end up being 0.4 plus 0.6 plus 0.9, and so that's 1.9, right? But optimally, if you put B, A, C, then you've got 0.3 plus 0.8 plus 0.6, which is 1.7. There's your counterexample.
I was confused about the keys have to be the ones that were.
Yeah, you have to keep it. And when you program this, by the way, next week, the keys are lexicographic order, so you sort them first, right? And that's the order that they need to be in. I don't know, did I just do it? I don't think I assigned, like, find a counterexample, like, for Gomer or something like that, but you just gave me a problem, right? Right. Gomer counterexample.
I'm looking at the Gomer questions, it takes me so long, I'm just like,
Nope. I was Gomer the other day, right? For thinking that you can just choose, what was the problem, the graph problem? That you could just, that you could just find a path, eliminate the path, find another path to formulate a cycle, right? And you guys found a counterexample for me. So thank you for that. Right? That becomes a Gomer question now. Right? Anyway, back to this. So the question is, which one is the root, right? So now that we've come up with a recurrence here, right, and we've come up with some corner cases, what we now need to formulate, not a recursion because we don't want the to pay for the recursion. What we need to do now is come up with a tableau, I and J. Right? Remember that I and J, I is going to run from 1 up to, excuse me, I need to make sure that this is right. I is going to run from 1 up to n plus 1, and J is going to run up from 0 up to n. Right? So it's going to be 0, 1, 2, 3, dot, 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 up to n, and 1, 2, 3, 4, dot, 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 up to n plus 1. Now, why is it like this? Because we want those corner cases. We want that. We want these corner cases where it's all 0. So in other words, if the right index is greater than the left index, then we know that it's an empty tree. What does that correspond to in our table here? It corresponds to the diagonal, right? So this is 0, 0, 0, 0, dot, 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 all the way down over here to 0. Now, what's the other base case here? It's when I and J are the same thing, and that will end up being the probability. Okay? So that's the probability of key 1. That's the probability of key 2. That's the probability of key 3, dot, 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 dot. And this is the probability of, here, let me put in one more there, probability of key n. Right? Now that we've got this table, all we have to do, those are my base conditions. Now that we've got this table, I just need to figure out how to fill this in. Where's my final solution? My final solution that I'm interested in is 1n, which is right here, 1n. Now, what are the dependencies, right? I can't just go ahead and fill this out top to bottom, left to right, like we did with the binomial coefficients. Why? Well, that would assume that if you do it the first row right here, like as it's written, right? Then what about all this stuff? Is it relevant? Yes, it is, right? So for that, I'm going to go ahead and bring in a nice photograph of it. Here we go. Here it is. Okay. There. So I want to compute C sub I j. you're going to be looking at values of L running from I plus 1, dot, 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 up to J. Right? Each one of those is going to be a cutoff. This one, for example, is when the left subtree is empty, and then you put everything else into the right subtree, I plus 1 through J. This one, at the other extreme, you put everything into the left subtree, right, and then leave nothing for the right subtree. Right? And then this one is your cutoff when it's I plus 1, right? This one is your cutoff when it's I plus 2, right? I plus 3, dot, dot, dot. This one, last one is when your cutoff is just J, okay? Or J minus 1, I guess, sorry. So in other words, this one and this one, in order to compute this one right here, you need all of these and you need all of these. So let's look at our table over here. In fact, I'll replace this with a better looking table. All right, there we go. All right. So these are, well, first of all of these down here are just irrelevant. You can go ahead and nullify them to 0 or not even compute them. But the diagonal is going to be all zeros. This next diagonal is going to be all the probabilities. And to compute this one, you need everything in the previous diagonal. So that suggests that we need to fill this table out top to bottom, or top left to bottom right, all the way up to here. Right? So in other words, let me look at, I'll bring in another actual example here. Here's a full table right here. Yeah, this is it. Here's a full table for a particular example, okay? The way that we would have to fill this out is, here are the oops, I wanted the red. Here are the probabilities, right? These are the probabilities. Right? Here's the next tier. Right? We need to compute all those. Then we compute all of these. Right, there we go. These two, and then finally this one. Right? Because this one is going to depend on all of these and all of these. This one depends on all of these and all of these. This one depends on all of these and all of these. So what we need to do is we need to go top left to bottom right and work our way up towards the top right. Okay? Now don't worry about figuring that out. I figured it out for you. Right? Here's the algorithm. Where's the full main algorithm? Right here. Okay. So to fill out this table, this is the initialization right here. Right. So this is. I'll annotate it in red here. This is the. Don't want that. Right. Well, no. Can I get it to look like that? All right, fine. Initialization. Right. These are empty trees. These are the next diagonal. Single node trees. This thing right here is keeps track of the root. We'll look at an actual example here in a moment. Right? That's keeping track of the root. And then we initialize yet another value here because the for loop up here doesn't take care of that one value. Okay. Now, how do we go top left to bottom right in a manner that we work upwards towards the top right? The way that I figured it out was just to use another variable, right? D stands for diagonal. Diagonal. Right? And then I compute my I and I compute my J as a value of I plus that diagonal. Right? Again, you just sit here and you stare at it for a while and, okay, well, if I is right here, what I need to do is I need to work my way down. So D will actually be my diagonal. I've got my I right here, and now I need to find my J. I need to run, 1, then 2, then 2, then 3, then 4, then 5, etc. Right. And so that's what these two loops are doing. What about the rest of this stuff? There we go. All right, so this one is doing that C sub ij, right? Being the, let me bring in, oops, oh no. I don't want to do that over, here we go, want this, the equation. Here we go. This is doing that equation right there, the one that we just wrote down. All right. The way that it's doing it is it's considering for each L, for L running from I up to J. We're going to compute Q right here, and then we're going to find the minimum among those. Whichever minimum gives us that value, we're also going to keep track of the root value L that gave that to us. That's going to be our root for that subtree. Why didn't I compute this sum right here? It does not depend on L. I compute it once at the end, right? And I'm taking the minimum among those and computing the sum right here. I output whatever was in the top right and this what's called a root table. Okay? As an example, let's take a look at this. This one is a result of, let's see, these probabilities right here. Here are the key probabilities. Choose any one of those boxes and let's figure out how it was done. So choose one of those boxes for me.
1,
1, 3, okay. This one right here, okay. C sub 1, 3. Remember, and I'm going to bring in, I'm losing real estate here, but I am going to bring in that that equation. We'll put it down over here, okay. Well, actually, first, before we look at that equation, let's notice something over here. I've got keys A, B, C, and D, D and E. Here are the probabilities. Those are on the diagonal, the upper diagonal right here, right? 0.2, 5, 4, 7, 1, 0, and 1, 2, 1, 2, 0. Okay, that's that diagonal right there. Right? I'm glad you didn't choose one of those, right? Because it would have been trivial. This is going to be the minimum as for L being 1, L being 2, L being 3 of these values right here. Right? In other words, this is going to depend on this value plus this value. 1, 2, 3. Yeah, sorry. Going back over here. This value and this value together. Why? Because that's going to correspond to C sub 1, L minus 1, which is 0, plus C sub L plus 1, which is 2, and then J here is 3, which is 1, 0, and 2, 3. These two values right there. Okay? And what value is that? Well, it's 0.587 plus 0, so it's 0.587. Right? What about when L is 2? Right? This is going to correspond to 2 C sub 1, and then L minus 1, which is going to be 1, plus C sub L is 2, so 3, 3. That doesn't look right. Yeah, 3, 3, isn't it? Right, so that's 1, 1, this one. I'll do a different color here. This one. And 3, 3. Is that right? Yeah, 3, 3. There we go. Those two together. And that's 7, 5, and then carry the 1, so 7, 6. 0.76. There we go. Is my math correct? Good so far? All right. And then 3 is going to correspond to where we've got C sub 1, and then L is 3, so it's going to be 2, plus C sub 4, 3. And I'll do yet another color here. Orange. There we go. So 1, 2 is going to be this one right here. Nope. 1, 2. And that and then that is compared to this one down here, 4, 3. And the value there is going to be 253. 253. 0.253. So which one wins out? The minimum is this guy right here. That's not where we get the number though, right? Remember, we're computing this one right here, 1.033. What else do we need to do? That summation, right? So what are the what's the sum of s going from 1 up to 3 of the probability of k of s? Well, that's just going to be these three values right here. The sum there is going to be 5, 6, 7, 8, 7, 8. So plus 0.780 gives me 9, 3, so 1, 0, 3, 3. Hey, it works out. That's the same value that we just computed. Right. So again, you've got something that looks like this. Where was it? There we go. You're looking at the far left one, and then you're looking at the one right below it. The next one looks at the one right next below it. Right? So you need all of these values. You need all of these values to compute this one. You need everything in the left, to the left of the value in that row. You need everything to below it in that column, meaning that you have to compute it in a top left to bottom right manner. And that's what this algorithm does. Okay. Now, what value gave us that minimum? That thing right there. Meaning that C should be the root among these three keys right here. In other words, we're going to put A and B over here, and C is going to be the root, and then we're going to do something else over here. Right? We keep track of that in this root table right here. Root table. Right. The root table for 1, 3, 1, 3 tells me 3, just like we computed right here. Right? Yeah.
So would this be a greedy solution as well? Because you look at the local optimum of like.
I mean, you're being greedy in one sense, but that's what optimization. I mean, all optimization problems, you're being greedy in some way, right? But you just can't be greedy immediately, right? I mean, terrible example, but the recent lottery win, right? $1.9 billion. Now, do you actually get $1.9 billion? No, that's the value if you take it over 30 years or whatever it is, right? You have the option of taking a lump sum, right? So, are you going to be greedy by saying, "Oh wow, 1.9 billion, I'll go ahead and take that"? No, right? The optimal way is to take the lump sum and invest it, because even at market prices, you're going to have more than $1.9 billion after 30 years, right? So, you look at the long term, right? You look at the long game rather than the short game, right? And when you look at the long game here, you end up, well, I'm not going to choose. Where was our counter example? Gomer. Where is it? Dang it. There we go. There's our counter example. I'm not going to be immediately greedy and choose A as my. I'm going to, wait. Let's hold off here. What if I did B and then A on the left and C on the right? Actually, that leads to a better solution overall, right? In the long term. Okay. So what about that root table? There we go. How do we construct the tree now? Right. Let's go ahead and start with a clean slide here. Where's that same thing? Where was it? Table example. There we go. All right. There we go. So remember that these are just indices, right? So A is equal to 1, B is equal to 2, C, D, E, right? 3, 4, 5. It doesn't really matter, right? Those are just indices. So what is the root of the entire thing? What is the root among 1 through 5? Well, you look at the table, 1 through 5, and you get 3. So 3 ends up being the root of the entire tree. Let me go ahead and replace that with the actual value there of C. Right? And now in the left subtree here, this is going to be everything containing A to B. And in the right subtree, This is going to be everything containing D through through E, excuse me. Right? So now your question changes. What is the optimal root of everything from A to B, from 1 to 2? 1, 2. It says that the root should be 1. In other words, it should be A. So let's replace that with A. Ugly. Right. And now you ask the question again. Well, what should be the left subtree here? Well, guess what? It's you're outside of the bounds of this root table now because there is no key there. Now you're asking, well, what's the optimal root for everything from 2 to 2? And guess what? It's just 2. B. Now ask the same question in the right subtree. What is the best root for 4 through 5 corresponding to C to D? And it says 5, which is going to be E. Oops. E. Right? And then D ends up being a left child, D, of E. Because you have to preserve those binary search tree properties, the key ordering. Right? There's the optimal binary search tree. There might be multiple optimal binary search trees. For example, one aberrant case would be, what if you had a normal distribution? What if everything was 0.2, 0.2, 0.2, 0.2, 0.2 for A, B, C, D, and E? Any balanced binary search tree is going to give you the same average number of comparisons, expected number of comparisons. Right? So there are some aberrant cases that you can take care of, but it doesn't really matter. Yeah.
Could you go back to that stuff? So we start from the top left corner.
Right.
So we.
This is the base case. This is the second base case. And then you fill it in top 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So you look at A to B first, and then you find A to B.
Yep.
Better one.
Well, you're searching for what's the best one from A to E, right? That's that one, but I don't know how to do that yet. To do that, I need everything in the left in that row to the left. I need everything in that column below it. So and likewise, if I just do this one, I need everything here and everything here. So I'm going to have to fill it in that way, right? And that's what those loops do. Really quickly here, let's analyze it. Here's the algorithm, main algorithm. Right. So this is just initialization. Ignore it. Right. What's our elementary operation? 12. I like that. Why? It's a comparison. You're trying to find the minimum. Okay, good. How many times do you do it? You do it for L running from I up to J, right? And you do one comparison, right? You do how many times? I is equal to 1 up to n minus d, right? And then you run d is 1 up to n minus 1. Right? Let's just do an overestimate on this. Yeah, why? How big is the table, first of all? N by n, so the table is of size n squared, right? Your little loop right here inside is at most n, right? Because sometimes, very often it'll be small, but sometimes it'll be large because you're for example, in the last one, you're considering all possible keys, right? And so this ends up being about order n cubed, right? About that's why it's big O. It's not going to be. I hesitate to call it theta, but that's just a loose comparison right there. Okay. Last piece of the puzzle here in the last 5 minutes, right? How do we go about building that tree? I'm just going to go ahead and give you the tree algorithm because it's a nice example of a in order walk through the tree, yeah, not in order, sorry, a pre-order traversal of the tree, but the tree doesn't exist yet. You build it as you go along. I always imagine, the cartoon where they're on a toy train, right? And they're running out of track. So what do? They just keep putting track in front of them, right? And you're building the tree as you do that. I'm going to build. I can't go to the right child, so I'll build the right child, and then I'll go to it, right? And then I'll back up, and I can't go to the left child, so I'll build the left child, and then I'll go to it, right? And that's what this is doing, right? But it's doing it in a pre-order traversal format, right? So to do that, it uses a stack, right? You start with the root key here, R1 to N, right? And you've created a new root node here. And then you push that triple onto the stack here. The root, and then the left and the right bounds of it, right? In general, you push a node U and its indices I and J. That is the root for keys I through J. Right? You pop that out, right? And then you ask a question. Well, what is the key corresponding to that root? Right? That's a lookup in the table. And then you have to ask yourself, well, if the left subtree is, right subtree is not empty, then you need to create it by creating a new node, setting its key according to that table right there, and then you set the right child, you use right child to this newly created node, right? And then you push those things so that you can jump to that node later and then create its two subtrees. Right? This is unconditional on the first one. It's not an else if, right? And it's not an else. You need to check, is there a right tree? Is there a left tree? Right? We push the right tree for later processing. And then we go on and say, well, is there a left tree as well? And do the same thing. The only difference being that V, this new node, becomes the left child of U. Right? Again, we don't have enough time, but if you want to, I've got that light table video series where I go through this algorithm in detail. Obviously, to build this tree, if it only has n nodes, it's going to be order n because it's a pre-order traversal. Right? All right. Practical considerations or implementation considerations. How are you going to do this in Python? Do we have a tree node already that you used in some other exercise? Don't we? Yeah. I built one in class, so you can use that. For Huffman coding, right? I thought we did, right? Oh, okay. Okay.
Because I would have just redone like the parsing code so that it didn't do nodes, it just did like the number as the node in network X.
Okay.
Node nodes using as the nodes.
Okay.
So it was like, I would have just redone it, but since we had to use DFS, I did not want to go through and like fix DFS to be not using those nodes.
Okay.
I just got it.
Yeah. You can always keep track of metadata, either internally with NetworkX or externally as a map or something like that. For this, I wouldn't even bother using NetworkX for this if it were me. In fact, I haven't. That's where I got the solution. Yeah.
Well, because balanced search trees are order log n. Is this much of an improvement?
Well, it's an improvement in the average number of keys. You're trying to optimize something different, right? With a balanced binary search tree, you're trying to optimize the depth of the tree or the height of the tree. You're trying to get it to be balanced. You're assuming that the cost of any one key, searching for any one key, is the same, that it's uniform. Here, it's not. Baseball is way more common than shinty, right? If you were Google, for example, and you wanted to rank your search terms so that more common search terms are, you find those quicker, right? Or you rank them up higher or something like that. Then, if a million people are searching for Astros baseball or something like that, and only 10 people want to know the shinty results, right? Then there's a clear winner there, right? And so that's what you're optimizing for. You're optimizing for that probability distribution.
So even though they're all log n, the number.
It could be that like this over here. It could be that your optimal configuration is a linked list, right? Like this one, right? The ABC just going down, depending on the distribution. Now, that distribution is assumed to be static, right? Fixed. You compute it up front, and it's not going to change. If it changes, right, then the tree has to change, and you have to reconfigure everything. So it's not a general purpose data structure, right? It is a very specific use case where you know the distribution is not uniform, and you want to optimize for the distribution, right? With just general keys, if you don't know the distribution, then you might as well go for a binary search tree, right? Over time, if you see that, well, it seems like more people are searching for baseball than they are shinty, then we can go ahead and collect that empirical data and come up with a probability distribution estimate, and then build our tree that way. Of course, over time, if that changes and shinty becomes way more popular than baseball, right? Then now we have to change everything. Right?
So basically, try to decrease the number per version.
The number of average key comparisons needed to find what you're looking for. All right. All right, we'll pick it up there with another example on Friday then. Oh, and then don't forget your